Welcome back to Chem Talk. Ready for another deep dive into the amazing world of chemistry.
You bet. Always excited to break down some cool concepts.
All right, so today we're tackling something called 6 to 5 periodic trends. Ionization energy.
Sounds pretty intense.
It might sound a little intimidating, but trust me, it's not that bad.
Yeah, and it's super important for high school chem students, especially around 10th grade.
Exactly. And by the end of this, you'll see how it helps explain why some elements are like the life of the party, always reacting, while others are total wallflowers.
Love that analogy.
So before we get into the party drama of the periodic table, can you give us a clear definition of ionization energy? What's it all about?
Sure. So think about it like this. Every atom has a nucleus, right?
Yeah, with those protons and neutrons hanging out in the center.
Right. And around the nucleus, we've got those negatively charged electrons. They're attracted to the positively charged nucleus, kind of like magnets, you know?
Opposites attract.
Exactly. So ionization energy is basically the amount of energy you need to use to overcome that attraction and kick an electron out of there.
Like giving an electron the boot.
You got it. And we measure this energy in kilojoules per mole, or kJ-mole.
So it's like a measure of how much effort it takes to pry that electron away from the atom.
Exactly.
But wait, wouldn't some electrons be harder to remove than others?
Absolutely. Some atoms hold onto their electrons much tighter than others.
Makes sense. So is it like those super strong magnets that are nearly impossible to pull apart? Like, do elements with more protons in the nucleus have higher ionization energy because they have a stronger pull on their electrons?
You're right on the money. More protons mean a stronger positive charge, so those electrons are clinging on for dear life.
Makes sense. But what about the size of the atom? I feel like that would play a role too, right? If the electrons are farther away from the nucleus, wouldn't the attraction be weaker?
You're thinking along the right lines. Size definitely matters. Think about it like this. As you move down a group on the periodic table, like going from lithium to sodium to potassium, the atoms get bigger, right?
Yeah, because they're adding more electron shells as you go down.
Right. And those outer electrons are farther away from the nucleus, so they're not feeling the love as strongly.
So the attraction is weaker.
Exactly. That's why ionization energy generally decreases as you go down a group. It's easier to snatch those electrons from the outer suburbs of the atom.
So it's like trying to hear a concert from the back row versus being right up front. The farther you are, the less intense the sound, right?
Perfect analogy. We call that the shielding effect in chemistry. Those inner electrons are like a crowd of people blocking the view.
So the outer electrons are kind of shielded from the full force of the nucleus.
Exactly. Just like those concert goers in the back rows.
Okay, so let me get this straight.
No.
Ionization energy generally increases as you move across a period from left to right because you're adding more protons and the pull on the electrons gets stronger. Yep, got it.
And it generally decreases as you move down a group from top to bottom because the atoms are getting bigger and the outer electrons are farther away from the nucleus, shielded from the full positive charge.
Perfect summary. You're a natural at this.
But here's the big question. Why should we even care about ionization energy? Like, what does it actually tell us about how elements behave in the real world?
Well, for starters, it gives us clues about an element's reactivity, whether it's a party animal or a wallflower, like we talked about earlier.
Oh, yeah. I'm curious. What makes an element reactive?
Well, elements with low ionization energy, like those alkali metals on the far left side of the periodic table, think of lithium, sodium, potassium, they're super eager to lose that outermost electron.
To make friends, I guess.
Kind of. They want to form positive ions and bond with other elements to achieve a more stable electron configuration.
Ah, so they're the social butterflies of the periodic table, always looking to mingle and share their electrons.
You could say that. But what about the opposite? What about elements with high ionization energy? Are they like the wallflowers at the party, content to just chill by themselves?
Pretty much. They're not giving up their electrons without a fight. Think about the noble gases on the far right side of the periodic table: helium, neon, argon. Their ionization energies are sky high. It's like trying to pull teeth to get an electron away from them.
So they're super stable and unreactive.
Exactly. They've already got a full outer shell of electrons. They're content with their solo act.
Gotcha. So basically, ionization energy helps us understand why some elements are eager to react and form compounds, while others are happy just hanging out on their own.
You got it. It's all about those electrons and how tightly they're held.
This is making so much sense now. It's like ionization energy is a key that unlocks the secrets of the periodic table.
I like that. Yeah, it's a fundamental concept that helps us predict how elements will interact with each other.
This is also fascinating. I'm already starting to see the world in a whole new light thanks to ionization energy.
I'm glad to hear that. It's amazing how such a seemingly simple concept can reveal so much about the elements and how they behave.
And speaking of seeing things in a new light, I'm curious to dive into some specific examples. Can we look at some elements with really high and really low ionization energies to see how this all plays out in the real world?
Absolutely. Let's explore some real-world examples and see how ionization energy shapes the chemistry around us. Okay, so let's start with an element that's making headlines these days, lithium.
Oh yeah, lithium-ion batteries. They're in everything from smartphones to electric cars.
Exactly. And it all comes down to lithium's low ionization energy.
Really? How so?
Well, lithium has an ionization energy of just 520 kilojmol.
That doesn't sound like a lot.
It's not. It means it's pretty easy to remove that outermost electron.
So lithium is like that friend who's always willing to share their stuff.
Kind of. Lithium readily forms positive ions, which, as we know, is crucial for battery operation.
So it's lithium's generosity with its electrons that makes it so valuable for batteries.
You got it. Now let's switch gears and look at an element with a really high ionization energy.
Okay, what do you have in mind?
How about helium?
The stuff that makes balloons float.
The one and only. Helium has a massive ionization energy of 2,373 kilojnali.
Wow, that's way higher than lithium.
It is. Over 4 times higher, in fact. You practically need a crowbar to pry an electron away from helium.
So helium's kind of a loner then, likes to keep its electrons to itself.
You could say that. Helium's high ionization energy makes it extremely stable and unreactive. That's why it's a noble gas.
Right, they're like the introverts of the periodic table.
Great analogy. They're perfectly happy with their full outer shell of electrons.
So we've got lithium, the eager sharer, and helium, the independent type. It's amazing how ionization energy can tell us so much about an element's personality.
It really is. It's a powerful concept that helps us predict and explain chemical behavior.
Now I'm wondering, is there a connection between ionization energy and electronegativity?
Good question. You remember what electronegativity is all about, right?
Yeah, it's like how strongly an atom attracts electrons to itself. Like fluorine has a really high electronegativity.
You got it. And you know what? Elements with high ionization energies usually have high electronegativities too.
Makes sense. If it's hard to remove an electron from an atom, that atom probably also has a strong grip on electrons when it's bonding with other atoms.
Exactly. It's all about those attractive forces.
So an element like fluorine, which is in the upper right corner of the periodic table, would have both high ionization energy and high electronegativity.
You nailed it. Fluorine is a real electron hog. It's the most electronegative element on the periodic table.
Wow. I'm starting to see how all these concepts are connected. Ionization energy isn't just about removing electrons, it's about understanding how atoms bond and interact with each other.
You're getting it. It's like a fundamental building block of chemistry.
And it's not just theoretical either. We talked about batteries, but what are some other real-world applications of ionization energy?
Well, think about solar panels. They rely on something called the photoelectric effect.
Photoelectric effect. That rings a bell, but I'm a little fuzzy on the details.
It's all about light knocking electrons loose from a metal surface.
Ah, and that requires energy, right?
Exactly. And the amount of energy needed is tied to the metal's ionization energy.
Oh, I see. So different metals will respond differently to light based on their ionization energies.
Right. That's why certain materials are better for solar panels. They have ionization energies that allow them to efficiently convert sunlight into electricity.
Wow, so ionization energy is at the heart of solar energy. That's incredible.
It really highlights how these fundamental concepts can have huge real-world implications.
I'm blown away. Ionization energy is everywhere.
It is. It pops up in all sorts of areas, from fluorescent lighting to mass spectrometry to astrophysics.
So it's not just about electrons and atoms, it's about understanding the universe.
You got it. It's all connected.
This has been an amazing deep dive.
Yeah.
You know, I had no idea that something as simple as removing an electron could be so complex and fascinating.
It's been a pleasure exploring it with you. There's always more to learn about chemistry, but ionization energy is a great starting point.
Now, hold on a second. We've been talking about removing a single electron from an atom, but can you remove more than one?
Ah, you're thinking like a true chemist. Yes, you can absolutely remove more than one electron. In theory, you could even remove all of them.
But that would take a ton of energy, right?
It would, and here's the thing. Each time you remove an electron, it gets harder to remove the next one.
Why is that?
Well, think about it. When you remove an electron, the atom becomes more positively charged.
Right, because you're taking away a negative charge.
Exactly. And that means the remaining electrons are held even more tightly by the nucleus.
Ah, so the more electrons you remove, the stronger the attraction between the nucleus and the remaining electrons.
Precisely. We call the energy required to remove a second electron the second ionization energy. The energy to remove a third is the third ionization energy, and so on.
And each successive ionization energy is higher than the one before it.
Exactly. It's like trying to separate magnets. The closer they are, the harder it is to pull them apart.
Great analogy. So while we often focus on the first ionization energy, it's important to remember that atoms can lose more than one electron.
Absolutely. And understanding those successive ionization energies gives us even more insight into the structure and behavior of atoms.
This has been an incredible deep dive into ionization energy. Who knew that something as seemingly simple as removing an electron could be so complex and revealing?
I'm glad you enjoyed it. It's a testament to the power of chemistry and the endless wonders of the scientific world.
It's amazing, isn't it, how much we can learn about an element just by knowing how much energy it takes to snag an electron from it.
Totally. It's like a little window into the atom's personality.
You know, it really blows my mind. It's like this tiny little electron can have such a huge impact on the properties of an element. Like whether it's a metal or a non-metal, whether it's reactive or not, whether it can conduct electricity or not, it all comes down to those electrons.
It really does. It's a reminder that even the smallest things in the universe can have a massive impact.
And you know, this deep dive has made me realize something else too. Chemistry isn't just about memorizing the periodic table or balancing equations. It's about understanding the underlying principles, the fundamental forces that govern how matter behaves.
Absolutely. It's about connecting the dots between the microscopic world of atoms and the macroscopic world that we see and experience every day.
So for any high schoolers out there who might be feeling a bit intimidated by chemistry, my advice is to focus on building a strong foundation.
Exactly. Start with the basics, like understanding atomic structure and the concept of ionization energy.
Yeah, it's like building a house.
Yeah.
You need a solid foundation before you can start adding walls and a roof.
Right. Once you have that solid foundation, you can start to explore more complex ideas like chemical bonding, reactions, and the amazing diversity of substances that make up our world.
Well, this has been an eye-opening deep dive into the world of ionization energy. I feel like I have a whole new appreciation for the power and the beauty of chemistry.
I'm so glad to hear that. And remember, there's always more to learn and explore.
To wrap things up, a big shout out to the Geeky Gamer Science teacher for putting this episode together and for making chemistry accessible and engaging for everyone.
Until next time, keep those electrons buzzing.